Hi everyone, welcome to week 4 of our course on the history of mathematics. This week we'll be talking about a couple of aspects of 19th and 20th century mathematics. In particular, we'll be talking about the size and stratification of the real numbers, and we'll also discuss some things about Fermat's last theorem. As a student of the history of mathematics, it's hard for me to understand how it took people so long to embrace certain number concepts. For instance, the idea of negative numbers, of irrational numbers, of complex numbers, and of the notion of infinity. These took a long time for people to wrap their heads around and accept. In particular, the idea that there could be different sizes of infinity was something that was discovered or embraced just in the 1890s, which is not too long ago. The person who's principally responsible for that is mathematician Georg Cantor. He showed that the real numbers are, in some sense, larger than the natural numbers, that is, the counting numbers starting from 1. And the way he did this is that he demonstrated that the real numbers cannot be put in an itemized list. You cannot exhaust the real numbers by saying that there's a first real number, then a second, and then a third, and so on. This was a revolutionary idea that somehow these two infinite sets, the real numbers and the natural numbers, could have somehow different sizes. And this had implications for various famous stratifications of the real numbers. For instance, we can break the real numbers into rational numbers and irrational numbers. It turns out that the rational numbers can be listed, first, second, third. The irrational numbers cannot. And what that means is that the irrational numbers are, in some sense, much larger than the rational numbers. Likewise, an algebraic number is a number that is the root of some polynomial with integer coefficients. The algebraic numbers can be listed. Numbers that are not algebraic are called transcendental. Examples of those numbers are like e and pi. Those numbers cannot be listed, and therefore the transcendental numbers are in some sense larger than these algebraic numbers. This is very counterintuitive because a lot of the numbers that we think about on a daily basis are rational and algebraic numbers. Then we'll move to the 20th century and talk a little bit about Fermat's last theorem. Fermat was a mathematician that lived, a French mathematician who lived in the early part of the 1600s. And he had a lot of interesting ideas about numbers, many of which were resolved by future mathematicians, but there was one conjecture he had that withstood the attempts of future mathematicians, and that is his last theorem. And what it says is that if you try to find non-zero numbers a, b, and c, such that a to the n plus b to the n equals c to the n, you'll never be able to do it if n is a number bigger than 2. If n is equal to 2, then of course we can find numbers a, b, and c. For instance, 3, 4, and 5 work. Now, this conjecture, which came to be known as Fermat's last theorem, withstood the attempts of many, many mathematicians until the 1990s, which is not too long ago, when Andrew Wiles, a Princeton mathematician, proved that Fermat's last theorem does indeed hold. And that is perhaps the most important or crowning achievement of 20th century mathematics. You might notice that in our book, Journey Through Genius, there is a portion of this book where the author discusses Fermat's last theorem and says that it has not been proved, and we know now that it has been proved. But remember that Journey Through Genius was published in 1990, before Andrew Wiles had proved Fermat's last theorem. Anyway, I hope that you enjoy this week's material, and best of luck.